Can everyone hear me all right? Thank you. So let me begin by thanking the organizers for the invitation to speak here and for organizing this wonderful conference. And I'm going to tell you more about normalization of instantons in the context of minimal superstring theory. This is based on a series of work with Dan Stefan Enicheku, who is a graduate student at Stanford, Raghu and Ashok, who are in the audience here, and Vivek Chakrabhavi, who is a graduate student at the University of Pennsylvania. So let me begin with some introduction. Let us consider the statistical sum over the closed string world sheets, where I have inserted no operators. So in that case, I can write the statistical sum as this sort of expansion over Z0 plus Z1 plus other terms. The Z0 term is given by the standard genus sum, so it's the exponential of something that scales like G string to the -2, which is your sphere, plus the torus, plus the 2 torus and other terms. However, non-perturbatively, this worldsheet will develop holes, and this is what is captured by the other terms in this expansion. So if I rewrite this in a more suggestive form, log of Z becomes log of ZZ, which is your standard genus sum, and then I have a Z1 over Z0. This term looks like e to the minus t, where t is the tension or the action of the instantons. It scales like a 1 over G string. And if you go back to your sort of first course on real analysis, it is obvious that this is not going to have a good perturbative series. And this e to the minus t is multiplied by some leading order coefficient that I will call the normalization. And then there are some subleading G string corrections. And the goal, the very modest goal for my talk today is going to be computing this normalization in the context of the type 0B minimal superstring theory and matching it with the dual matrix integral. Just some historical background on what has happened in this area for the non-experts. So this kind of non-perturbative effects were first studied in the context of two-dimensional critical string theory by Balthazar Rodriguez and Yin and Ashok Sen. And then these kinds of computations have also been generalized to 10D superstring theory and its various compactifications. So in terms of the lay of the land, the talk is basically divided into 3 sections. So I will begin first by describing for you the dual matrix integrals. Then as an aside, I will talk about the computations in the context of minimal string theory. The reason being that everything is a little bit easier to describe. And then finally, I will go on to generalize everything to minimal superstring theory. So any questions before I get started? Okay. So for the 2,4K family of minimal superstring theories, the duals are given by unitary matrix integrals that I need to take the double scaling limit for. So in general, a unitary matrix integral takes the form shown here, where du is the standard measure, n is the size of the square matrix, g is the 't Hooft coupling, and the potential is the term that I've shown in the square brackets. So there are some other couplings, these TL pluses and minuses that show up here. And in the special case of k equals 1, we get the Gross-Witten-Wadia model, which was first described in the context of two-dimensional lattice gauge theories. So all of these models for, as I change the couplings, have this gap closing phase transition. So if you consider the V coupling phase where G is very small, so because it shows up in the denominator in the potential is really strong. And what happens in that case is that all the eigenvalues really want to sit at the minimum of the potential. So they condense to a droplet on the unit circle. And as I make G larger and larger, the Vandermonde repulsion starts to take over and it starts spreading the eigenvalues out. And at some critical value of G, there is a gap closing phase transition where the gap closes. So this is a feature that is sort of specific to unitary matrix integrals. There is nothing like this in Hermitian matrix integrals because you have the whole real line. So there is no phase transition. So this is one of the subtleties that one has to deal with when talking about these kinds of models. So let's start with the V coupling phase where you have the gap. In the double scaling limit, we want the spectral curve of the unitary matrix integral to match that comes from the minimal string theory. So this is given by this particular two-sheeted Riemann surface. where U is the Chebyshev of the second kind. This Y has a branch cut discontinuity, and the density of states is basically given by considering this branch cut discontinuity in Y. So this is the form of the density of states. Notice that it's only supported for values of X that are greater than 1 or less than -1. And this is precisely sort of the gap that I showed you. So this is what a representative density of state looks like. And the effective potential, which is the combination of the potential that sort of the eigenvalues have and the van der Waals repulsion from everything else that the eigenvalues feel, is given by this form. This e to the s naught scales like 1 over g string, and it's sort of the genus counting parameter in this case. And that is what the real part of the effective potential looks like. So it's 0 on the cut, and then in this gap, it sort of has this oscillatory behavior. The saddle point equation for the eigenvalues is given by V effective prime vanishing. And so you can see a bunch of these points here, these extremal points, which correspond to the zeros of the derivative of the V effective, and those will be the locations of my eigenvalue instantons. So the zeros of the Chebyshev give me the locations of the eigenvalue instantons, and there are 2k minus 1 of them. And I've shown the figure for k equals 3, so you can see the 5 different eigenvalue instantons in this case. So to compute the normalization, you need to do a Gaussian integral that you evaluate by saddle point around these extrema. The steepest descent contour actually passes in the imaginary x direction, which is why you have this sort of factor of I floating around. And the other thing to notice here is this double derivative of V effective that shows up in the denominator, and that comes from the standard Gaussian integral. So I can re-express this normalization times the V effective raised to power half as some pure number. And the goal is basically now to match this pure number to a number that we get from the string theory computation. A similar story holds in the strong coupling phase, modulo some subtleties. So again, this is what the spectral curves looks like. In this case, because it's some function squared, it's a reducible algebraic curve, and it splits into 2 different branches, y plus and y minus, which are just related up to a minus sign. So in this case, the density of states is given by the difference between y plus and y minus, and it's supported on the entire real line. So there is no gap here as expected. And in addition to the standard eigenvalue instantons, there are also ghost instantons. This is something Raghu mentioned in his talk yesterday as well. So this was first pointed out by Moreno, Schiappa, and Schwick. And the idea is that the positive effective potential is naturally defined in the upper half plane. However, I can analytically continue it to the lower half plane. And that gives me some additional extrema, which I will label as the ghosts. So the conventions that we use will be the following. The instantons that correspond to the positive effective potential will be called positively charged. So 1 comma n and this 1 comma n bar ghost are both positively charged. And then the guys that correspond to the negative effective potential will be negatively charged. And what ghosting does is it keeps you at the same location, but it changes from V effective plus to V effective minus. So it sends 1 comma n to 1 comma n ghost. And that sort of has the additional effect of changing the charge of my instanton. Again, as earlier, the zeros of this polynomial give the locations of the eigenvalue instantons. So both xn and xn ghost live in the upper half plane, and the barred guys live in the lower half plane. And in this case, there are k positively charged real instantons and k negatively charged real instantons. In this case, the leading order correction is actually due to a pair of instantons for reasons of charge conservation. So this is what the representative answers look like. So the first answer is for the normalization between a real positively charged instanton and a real negatively charged instanton, and the second line is an expression for a real positively charged instanton and a ghost negatively charged instanton. So this concludes sort of the first part of my talk. Any questions? Okay. Let me sort of now go on to my aside, which is about minimal string theory. So the theory consists of 3 ingredients. The first ingredient is a Liouville CFT. I have flashed the action for you. B is some real parameter. And this guy has a central charge that is bigger than 25. The next ingredient are these P prime comma P minimal models. These are some models which have finite number of Virasoro primaries. The central charge is given here. And the central charge in this case is less than 1. In particular, for the 2,3 case, the matter sector, this minimal model completely goes away, and you have something called pure gravity. And then the third thing is the BC ghosts, which have central charge of minus 26. And these 3 constituents are just linked by the constraint that the total central charge needs to vanish. And that relates for me the B that shows up in the Liouville CFT and the parameters P prime and P that show up in the minimal model. This is the particular relationship between these quantities. Now, the Liouville CFT has 2 classes of boundary conditions. One of them are the FZZT labels, which are labeled by some cosmological constant mu b. And then there are the ZZ labels, which are labeled by 2 integers m and n, satisfying certain constraints. And you generally solve for these ZZ boundary conditions using some sort of bootstrap conditions. So the non-perturbative effects on the minimal string theory side are represented by the surfaces that have ZZ boundaries. The T in this case corresponds to the tension of the ZZ brane, which you can roughly think of as the disk amplitude with nothing inserted into it. Okay, so this is what a representative figure for Z1 over Z0 looks like. So once you have this ZZ brane, you can have 1 cylinder on the brane, you can have 2 cylinders, you can have as many as you like. And I can recast this in a form where I have sort of the answer coming from the brane, which is e to the minus t, and then everything else, which is the normalization, which will be given by the exponential of the cylinder. So the goal will be to compute the cylinder or annulus partition function in this particular context. What do you mean?
Why don't the cylinders like merge like in string theory? You would expect that, you know, you'd get a 3 boundary diagram, a 4 boundary diagram, and
right,
so on.
Those are all subleading in G string. So at the leading order, they don't contribute. So it's captured by this sort of plus 1 over or like this order G string piece.
All right, thanks.
Yeah. Okay. So for the purposes of the talk, I will specialize to the case of pure gravity. So let us call T as the open string time, and then Q is the standard e to the minus 2 pi t. The first constituent is the Liouville annulus partition function. I choose 1, 1 boundary conditions because in this case, those are the only boundary conditions available to me. And this is what the Liouville annulus looks like. As I said, the matter is trivial, so the matter annulus is just 1. And then I get some contribution from the ghosts as well. So the thing that I now want to compute is the exponential of the cylinder, where the cylinder is given by integrating over the modulus, which is the open string time. The measure in this case is dt over t. The factor of 2 comes from the fact that it's a symmetry factor coming from the fact that both of the boundaries of my annulus are the same. And then this ft is a combination of the 3 different annulus partition functions. So it is some sort of power series in Q. Okay. So already at this level, there is a question, because if you recall the answer in the matrix model cases, the normalization came with a v effective to the minus half, which means that the normalization scales like a square root of G string. And here there is no G string appearing. So here my expectation is f might be a pure number, which means that the normalization will be a pure number. So it scales like G string to the 0. So there's already a question of how am I going to get that factor of the square root of G string. And if you look at this a little bit more carefully, there's a bigger problem, which is that at the t goes to 0 and everything is regular, However, in the t goes to infinity limit, there is a IR divergence. And this comes from the fact that f of t has this expansion to leading order in t. So there is a e to the 2 pi t, which gives me an exponential divergence. And there is a minus 2, which gives me a logarithmic divergence. So not only do I have to explain the sort of factor of square root of G string, but I also need to regulate these divergence. And that's precisely where a string field theory comes in to solve the problem for us. So string field theory is a very scary word for most people, and I'm going to use a very light version of it, so don't be scared. So the first thing is, in general, this f of t takes the following form, where it's a sum over the bosonic modes or minus a sum over the fermionic modes. And if I put this into my answer for n here, and I just sort of ordinarily do these integrals, I can just get an answer for n which looks like the product over the hf hats raised to power half divided by a product over the hb's. The fermionic guys come in pairs, which is what the sort of second equality is telling me. So I only need to sum over half of them, and the square root for the hf hat goes away. And now I can recast this in a form that comes from the open string field. So the bosonic terms just become some sort of ordinary Gaussian integrals over the bosonic open string fields. And the hf hats correspond to a pair of fermionic open string fields. So this is all good if my hb's and hf hats were all positive, and I will run into issues when these are either negative or zero, and which are exactly the cases that were leading to those divergences. So now I just need to tell you how to handle the cases where HB or HF hat are non-positive. So this is a list of the culprit states that I need to care about. So the first two lines are the tachyonic states. In particular, the first line is precisely the state that was giving me this factor of e to the 2 pi t. The next four lines are the zero modes. And so this zero state and C1, C minus 1 of zero state are the states that were giving me those factors of minus 2. So I should point out a couple of other things here. The first thing is that the only states that are contributing are the ones that live in Siegel gauge. So Siegel gauge condition just tells me that B0 acting on the state vanishes. And those are precisely the states that show up in sort of the ordinary string field theory expansion. And the other thing is that, as I sort of maybe already alluded to, C1 acting on 0, which is the first line, is Grassmann even, so it's bosonic. And then 0 and C1, C minus 1 acting on 0 are Grassmann odd, so those are my fermionic modes giving me the factor of minus 2. So I basically need to tell you how to regulate these states, which are the culprits here. So for phi 1, sort of doing the simplest, dumbest thing kind of works, which is I just rotate the contour to be along the imaginary axis. So now what used to be a divergent integral sort of becomes perfectly fine, and I can just do the ordinary Gaussian integral to get a factor of I. I should point out that there are maybe some ambiguities coming from what contours to choose here, and this is not an issue for us, because there is precisely the same ambiguity that lives in the matrix model, where for those minimal steepest descent contour integrals that I was doing, I sort of had the same ambiguity. And when I'm actually looking at the full partition function, there could be some factors of plus minus 1 or plus minus half that show up, or even 0 if this particular contour or instanton is not contributing. So the match will now be for a particular choice of contours on the string theory side, which are matched with an analogous choice of contours on the matrix model side. So I will always choose my contours to be in this particular way. Okay, so that sort of takes care of the easy part, which is the phi 1. The hard part is taking care of the P1 and Q1 modes. In that case, the Siegel gauge choice actually breaks down, and we need to change the fields to a different class, and that's what I'm going to explain next. So if you had an ordinary DP brane, this 0 would actually become sort of the momentum labeled states, and you would have done an integral over all of the momentum modes, which you could have ordinarily sort of regulated using some sort of epsilon prescription. So let's go forward with this K case and see what's happening. So the fields that live in the world volume gauge theory path integral are of this form. So you have a gauge field piece, which looks like a mu k. And then you also have this sort of psi k piece. And in this case, what happens is there's these fields gauge transform. So a mu transforms by sort of the standard k mu times theta k, where theta k is the gauge transformation parameter. And then this psi k transforms to psi k plus k squared theta k. We use this gauge freedom, sorry, I'm missing a line. So we use the gauge freedom to set this psi k to vanish. And this introduces the Faddeev-Popov ghosts, which were precisely these P and Q fields that were the culprits. For d instantons, k is set to 0 rigidly. So I cannot use this sort of second line gauge transformation to set psi k to 0, because psi just goes to psi. What this means is that my Siegel gauge choice is broken down. I do not need to introduce the Faddeev-Popov ghosts. I need to sort of do everything in the sort of ordinary way, where I integrate over my classical fields using ordinary path integral tools and divide by the volume of the gauge group. So my integral over P1 Q1 is actually replaced by an integral over psi1, and I divide by the volume of the gauge group. The top integral now is just an ordinary Gaussian integral, so you get the standard answer. To compute the volume of the gauge group, this theta parameter is now related to the rigid U1 theta that lives on the d instanton. And from there, you can figure out that the volume of this gauge group is 2 pi over GO, where GO is the open string coupling of the sort of 3-point diagram. And then using results from tachyon condensation, you can recast this in terms of the tension. So the much awaited dependency on the tension has shown up. So this is where this square root of G-string dependence that I was extremely worried about comes into the picture. Okay, so once I have all of these tools, I can just combine the three pieces together. So the first factor of I comes from the bosonic regulation. The second piece comes from these zero modes being regulated. And then there's a finite piece. And I get an answer that has the sort of right scaling with the tension. And this precisely matches the result, which in this case comes from a dual Hermitian matrix model. These computations can also be generalized to sort of higher versions of this minimal string theory labeled by some p prime comma p, and it generalizes both to single and multi-instantons. And a similar match also holds in the case of Virasoro minimal string. In that case, it was a little bit interesting because we did not know what the ZZ states were for this time-like Liouville that was being proposed. And I think this match was precisely the thing they used to identify the ZZ boundary conditions in the time-like Liouville. So any questions about that before I move on to minimal superstrings? So again, like the minimal string case, my minimal superstring will consist of 3 ingredients. The first one is a n equals 1 super Liouville theory. This is the central charge. In this case, the cosmological constant can take either sign, and the sign of the cosmological constant corresponds to whether I am in the gapped phase or the ungapped phase. So positive mu corresponds to the weak coupling or the gapped phase, and then negative mu corresponds to the strong coupling or the ungapped phase. The second ingredient is the 2,4K minimal superconformal field theory. This is the central charge for that guy. Again, this has a finite number of Virasoro primaries. Those will sort of come either with NS or R flavor. And in the 2,4 case, again, this matter sector becomes completely trivial. And I get something which is called the pure supergravity theory. The last thing I have are my standard BC ghosts plus the beta gamma ghosts. Those have central charge minus 26 plus 11, which adds up to minus 15. And again, if I impose the condition that the total central charge needs to vanish, I get the value of P, which looks like 1 over square root of 2K. Okay. So now taking some inspiration from what I had in the minimal string case, let me first sort of describe for you how to regulate everything that was giving me the divergences. So the annulus partition function, again, will have divergences from open string states that have the L0 eigenvalue being non-positive. For things that are tachyonic, so L0 is given by some h, which is less than 0, I am again going to rotate my contour. That is going to do the job for me, and I get an answer that looks like I over square root of minus h. The culprit states for the L0 equals 0 case are these guys over here, where this minus 1 is given by e to the minus phi 0. Phi is one of the fields, sorry, this var phi is one of the fields that shows up in the bosonization of the beta gamma system. And this is the NS vacuum state. As earlier, again, Siegel gauge is going to break down. So these two states, which are the culprits, are going to be replaced by the ghost number 1 state, which is the psi in this case. So the replacement rule just tells me that whenever I have this P1 Q1 integral, I will replace this by a psi integral and divide by the volume of the gauge group. And I get an answer that looks incredibly similar to the answer I had in the minimal string case. So these are the two inputs I have from string field theory in this case as well. Okay, so I think the replacement procedure works for both the weak coupling, which does not have anti-instantons, and also for the strong coupling, which has anti-instantons. So yeah, I'll comment on, because in that case, the tensions can be different if you have different kinds of instantons, but I think there's a unique way to identify which zero modes correspond to which branes. Okay, so again, I'm going to specialize to 2,4, but everything will go through in the 2,4K case. I'm just doing this for the sake of simplicity. So in the weak coupling phase, we just have one ZZ state, which is this 1, 2 state. In the strong coupling phase, we have a pair of these instanton anti-instantons, and then we also have the corresponding ghosts. So let's start with weak coupling. Again, the matter sector is trivial. So there is a NS sector contribution that looks like this. So there is some Liouville annulus that you have, and there's some ghost annulus that you have. You combine them, you get something. This will have the divergences. You regulate them using the standard regulators. The only reason I want to flash this slide is to talk about the R sector, because there are a bunch of sort of physically interesting minus signs that one needs to care about. So in the R sector, again, there is the annulus. Both of these minus signs that show up here are physically interesting. So the minus sign that shows up in the Liouville sector actually comes from the fact that you first need to write down the annulus for a pair of FZZT branes. And then when you analytically continue them and substitute the values of the ZZ branes, you get some factors of I, and that gives you this minus sign. So this is a physically interesting minus sign. In the second line, the ghost contribution also has a minus sign, and that has to do with the fact that this e to the minus var phi state that I showed you actually is odd under GSO. And so this is sort of the standard minus sign that might even show up in 10-dimensional type 2 superstring theory when you're considering, say, the torus or the annulus in type 2b description. So it's the minus sign that shows up between theta 3 to the 4 minus theta 4 to the 4. So it's the similar sort of kind of minus sign that shows up. Okay, so again, what one needs to do is combine both of these contributions, use the standard string field theory replacement rules. The first line comes from replacing the bosonic modes. The second line comes from replacing these zero modes, and then everything else is the finite piece. I get an answer that matches perfectly with the matrix integral. And actually, there is another way of getting this answer up to these sort of factors of half that comes from resurgence theory. and it also matches the resurgence answer. So in the general 2,4K case also, we have an exact match with the matrix integral, and this is what the answer looks like in that case. So here there's sort of none of those subtleties which have to do with identifying where which zero modes come from, because there's just one brane here. Okay, let's move forward to strong coupling. And this is what the various ZZ states look like. I just flashed the slide to sort of identify for you what the various, where the various things come from. So in this case, the charge of the brane corresponds to whether the R state has a plus or a minus sign. So the first line and the fourth line are positively charged states, and the second and the third line are negatively charged state. And the ghosting, what ghosting does for you is it multiplies the whole state by a factor of -1. So it takes you from the first line to the third line and takes you from the second line to the fourth line. And that's related by a multiplication by a -1. So let's think about what happens to the annulus between the 1,1 guy and the 1,1 bar guy. In that case, you have the full NS annulus that gets 3 contributions. So there are the term that connects the 1,1 to the 1,1. That's the first term. The factor of half is a symmetry factor. The second line, the second guy comes from the annulus between the 1,1 bar connecting to the 1,1 bar. Again, there is a symmetry factor of a half. And the third guy is coming from the 1,1 connecting to the 1,1 bar. Those are different, so no symmetry factors. So I get some result for the NS sector piece. And then in the R sector, what ends up happening is that because of this sort of minus sign that was placed, the cross cylinder cancels against the two ordinary cylinders. So this normalization only gets a contribution from the NS sector. And once I sort of do all the computations and dust settles, this is what the final result is. This, again, this factor of -4 up front is a 2i squared coming from the bosonic tachyon. The second piece comes from sort of 2 pairs of zero modes, and the third piece is a finite guy. And again, I get something that matches exactly with the matrix model. This is what the generalization looks like. And coming back to Ashok's question, I can precisely identify the only things that actually have the zero modes are the first sort of NS plus R terms and the second NS plus R terms. And so I can precisely identify that there is a T to the -1/2 corresponding to the first brane, and then there is a T to the -1/2 corresponding to the second brane, even if those branes did not have the same tension. Okay. The next thing I want to point out is that these were all 2 instanton contributions. What happens in this case is that the single instanton contribution vanishes because the R sector annulus is divergent. And this is what that particular divergence looks like in the closed string channel. So S is the closed string time, which is 1/T. And this has a divergence. So this AR guy looks like -infinity. So exponential of AR looks like 0, which is why there is no single instanton contribution in this case. And versions of this were also noticed in the C hat equals 1 case. More physically, the reasoning is basically that the state carries some overall RR charge, and we will need a neutral brane anti-brane combination to get a non-zero answer. So this even persists for other diagrams. So if I have a non-matched number of branes and anti-branes, I will always expect the answer to be 0. Okay, so maybe I'm sort of doing too well on time, so let me conclude. What we've been able to do is we've matched the instanton contributions across this duality between minimal superstring and matrix integrals. And this match actually also holds for a multi-instanton configuration. So if you have multiple ZZ branes and multiple sort of annuluses connecting them, the only additional thing you need to actually compute is the cylinder connecting ZZ branes of different types. Those usually don't have divergences. So you don't even have to worry about string field theory in those cases. And in terms of future directions, the first thing to do would be to develop a deeper understanding of these ghost branes. And the second thing is actually If I send k to infinity and do a particular zoom in, I actually get the n equals 1 super jt. And studying this phase transition in that case seems like an interesting problem. So Stanford and Witten actually studied what happens in the strong coupling case. And then Rosso and Turiachi pointed out what was going on for weak coupling. And right now we believe that in the weak coupling phase, what's happening is actually there's some sort of breaking of supersymmetry. And if you actually zoom in towards one edge of the eigenvalue cut, you sort of lose information about the other edge, and it becomes just ordinary JT. But that's sort of conjectural, and one really needs to understand this in better detail. So let me conclude with that.
Right, we have time for questions.
Yeah, maybe you explained it, but I missed it. What exactly is the difference in the worldsheet description for between the strong and the weak coupling? So these are different Liouville theories?
So the main difference is coming from the sign of mu. So I think what is the normalizable mode also changes between these Liouville's. And I think that sort of causes a difference between the two theories.
I see. And there is no analog of this for the bosonic case?
I don't think so. There's no
I see.
analog of this.
Okay. Okay, thank you.
Oh, well, okay. In the non-supersymmetric setting, at one point you restricted your attention to the pure gravity 2,3 minimal model. I didn't catch if, does this hold for a more general configuration of the minimal models in the time-like Liouville?
That's right. So it holds for the whole family of p prime comma p, which is the whole family that you get here.
Oh, okay, I
All
see.
the c less than 1 models. And then also folks show that holds for a minimal string as well.
So is it possible to like concisely say why the 2,3 is easier to present and what changes in the p prime comma p setting?
So A, there is the whole matter sector. B, there are a lot more ZZ states. So it's just keeping track of a lot more things, basically. So it's just more labels that I need to write down on the slides. I don't have a good intuitive understanding. They're not that mysterious in the sense that if you want to get the right answer for the Gross-Witten-Wardia model, actually, the correction that you get from the real instantons is exponentially enhanced. So you really need these ghosts even to get the right non-perturbative answer in the sort of simple Gross-Witten-Wardia model. Like even there, if you don't have ghosts, you will get something that's exponentially enhanced instead of exponentially suppressed. So the only thing it's doing for you is changing the sign of V effective, essentially. And that changes an exponential enhancement to an exponential suppression. Does that satisfy you?
An engineering answer to the question. I was wondering if there's a more like intuitive answer.
Yeah, I don't have a deeper understanding, unfortunately.
Any more questions?
I mean, physical understanding of this, why this is the case, right? That you have to deform the original contour to the instanton, and so for some things it's possible and for some others it's not possible. I mean, that can be done for every case. There's a contour deformation argument because not every instanton may appear in the original integration contour, right?
Right, so yeah, I think that is correct. Even in this case, the ghosts might be somewhat natural if you do a contour deformation. That's correct.
Those lines, I thought what Raghu did show for his case was that the contour of steepest descent did pass through the instantons, which gave the exponential suppression, right? The ghost instantons. And
The ones which gives exponential enhancement.
exactly,
Yeah.
exactly. So that is true, presumably here. You
That
can
is
show
also
that.
true in the matrix model here, that's right. But I don't know what the analog for string theory is because I'm not sure what the contour deformations in that case will sort of look like more naturally.
Okay, if there are no further questions, let's thank Chitraang.